Hey guys, this is just going to be a short video in order to be able to help you out with doing some stats practice. We talked about the three families of statistics, the chi-squared, t-test, and correlation. This is on 0.4.5 stats practice on your Canvas classroom. And you can watch this video to help you remind yourself of what these three families are. So I'm not going to go over that right now. What I am going to go over is how to do some of these calculations. So we start off with the correlation calculation. Click on this in order to be able to pull up some information on the correlation calculation, which we'll look at in just a second. This is basically just sort of explaining to you what this really means. We're going to go ahead and dive right in. So the next thing you're going to click in is this link right here, and it's going to take you to, and let me go ahead and take it back to the home so you can see. It's going to take you to this home, and basically DSL is a website that allows you to be able to have access to all kinds of data sets, and these are really good for practicing statistical analysis. And we can actually go in and choose what kind of statistical analysis we want. So we're going to start with correlation. And because I like burgers, we're going to choose the burgers one. So correlation is a really great way to compare two quantitative, or continuous or measurable variables that are typically going to be like a number, right, specific number. And essentially you're just saying, does this variable affect the other variable? Are they correlated, right? Are they related in any way, shape, or form? So if we look over here, my question is going to be, is the amount of fat in burgers correlated at all to the amount of sodium in burgers? In other words, as the amount of fat goes up in the burgers, like if I compare burgers, will sodium likewise increase between the burgers, or as fat goes up, will sodium decrease, or is there just no relationship between the amount of fat and the amount of sodium in a burger? So I want to know this. So what I do is I'm going to go ahead and open the spreadsheet. Now the spreadsheet for you guys is going to be in the bottom of this actual assignment. For me, I created a different one, separate one, just for practice. And so you can see here, I've gone ahead and I've chosen the two variables I want to compare. I'm comparing fat and sodium, right? So these are the only two columns I'm concerned with. They give me calories, but I'm not comparing calories. Now it would be interesting, to come back and see whether or not the amount of fat was related to the amount of calories. I would assume yes, but I of course can't know for certain. And so you can do that later if you want to, but for right now I'm trying to look at fat and sodium, that correlation together. Maybe I'll use the other correlation to compare. That'd be kind of cool. Okay, so I go ahead and I plug in the data points. So I basically look at these and I plug them into my spreadsheet, and I create little columns to make sure I know what I'm looking at here. I got my fat as my x variable and my sodium as my y. And then I'm going to go ahead and run something called the Pearson's R. And basically the Pearson's R is going to be a way to show whether or not two variables are correlated. So fat and sodium, are they related? And are they positively related, negatively related, or inversely related, some people say, or is there no relationship really between them? So in looking at this, how I do that is I'm going to go ahead and use Google Sheets built-in way of actually doing calculations. So I'm going to press equal sign, which is how you start any calculation. And then I'm going to go ahead and type in CORREL. You're going to see this come up right here, Pearson's correlation coefficient. Now essentially what that is, and you can go ahead and turn on the formula help, it's going to describe to you, this is going to be a formula that's going to help us to actually determine statistically whether or not this fat is related to the sodium in these burgers. So it's going to ask me to be able to look at data set 1 versus data set 2. Okay, now it says data y versus data x. So if this is my Y data group, then I'm going to go ahead and start with this one. Now, how do you define a data set? Well, the Sheets is going to look at this not as numbers, but as cells. What do I mean by a cell? A cell is any one of these rectangles or squares. So this is where 920 is. This is cell B2. Right, and 1500 is in cell B3, etc. So it's going to be thinking about it in terms of cells, not numbers. So you're going to want to define it in terms of cells. So B2 is, you'll see as soon as I type that in here, it lights this one up. That's the first one in my data set, and my data set extends all the way down from B2 all the way down to B8 for my Y variable. So I'm going to go ahead and press colon, which means all the way through. And then I'm going to say B8. And you can see, so I've gone ahead and highlighted all of my data sets from B2 to B8. That's my first data set, okay? Then I'm going to press comma to distinguish it. Now my second one is going to be my X data set. So for this one, I'm going to go ahead and type in, this one starts at A2, so I'm going to type in A2, and then I'm going to go all the way through A8, just like the other one, and then close the parentheses. Once I do that, I'm going to be able to click enter, and then here I have the Pearson's R correlation coefficient. Now, what does this mean? It basically means that this is in here. Let me go ahead and I'll show you. So this goes from -1 to +1. Okay, so Pearson's is a scale. Okay, so here we have the hang on, let's show this to us first. All right, Pearson's scale goes from -1 to 1. Okay, so what does this mean? At 1, we have a perfect positive relationship between the two variables. In other words, if fat increases, sodium definitely increases. Okay, there's a 1-to-1 sort of correlation between them. We have an inverse or negative correlation if the opposite is true. So if there's a -1, it's a perfect negative relationship. In other words, as the fat goes up, sodium goes down, or as the sodium goes up, the fat goes down. Either of those two, right? At r equals 0, or around here, there is no relationship between the two variables. These are known in these intermediary areas between 0 and 1 and 0 and -1. These are what we call weak correlations, right? So there might be some relationship, but there's really not much. Really, the closer we are to 0, anywhere around here, this is very highly suspect, and usually we say that that's not very likely to be an actual correlation or relationship. So what we're seeing might just be noise in the data, okay, if there is any kind of relationship whatsoever. So we're going to go ahead and take a look at how this actually manifests. So over here we see we have 0.1. Now 0.1 is very low. It's almost 0.2, but still it's somewhere down here, so it's very close to 0. So we could probably say that the amount of fat in these burgers is really not correlated or related very much at all to the amount of sodium. But we don't want to stop there. We're actually going to go to Pearson's R-squared. And the R-squared is a great value because Pearson's R-squared goes from 0 to 1. And it's basically going to say how much of the variance of your data, so how much of the variation of your data in your x value is explained, in your y value, excuse me, is explained by your x. So in other words, it's basically looking at how well these this formula in what you've chosen, right, the variables you've chosen actually fit to the data, right? And this is an important question because if we don't fit our question to the data, basically we're saying that what we were examining wasn't really representative of the situation anyway. In other words, it's kind of a mathematical way of saying, you kind of set this up in a really stupid way, right? And so, you know, no wonder you didn't get a correlation or anything at all, you dummy. These two are not related whatsoever, okay? So we're going to take a look at Pearson's R-squared, which is basically going to tell us that. So the way Pearson's R-squared works is it's just this number squared. Pearson's R squared. Simple. So how do we square the number that's in here and put it over here? Okay, well, we're going to press equals because we know that's how we start an equation. And we know we need to square this number. Now again, the spreadsheet's not remembering this as a number, it's remembering this as a cell. This is cell D3, okay? So I'm going to go ahead and put D3 in parentheses, and all of a sudden you're going to see it light up, right? Now, if I press Shift and 6, I should get this weird little caret key. That's the little key that you use to indicate an exponent. And then, of course, because it's squared, I'm going to put a 2. And boom, we get Pearson's R-squared. And we can see that that's very close to 0. Now, 0 is not very good of a fit whatsoever. And really what it's saying is that the variance that we see in our y data based off our x data is not very much different than just the average that we would expect if it was totally random. And so basically this means that it's probably just kind of totally random. Any of the little bit of correlation that we might see is really just explained away by noise in the data. So it's not really that great. Okay, now let's go ahead and let's take a look at the other one though. So I like the other idea of taking the fat and comparing it to the amount of calories. So what I'm going to do is I'm going to go ahead and copy this, and I'm going to kind of paste it down here again. And then I'm going to run a second example, but over here I'm going to go ahead and look at the calories. Is going to be my y value, and I'm going to go ahead and plug these in. So 410, 580, 590. I'm sorry, it's a little bit on the fly here, this idea. 570, 640, 680. And then there's one more, which is 660. All right. So we got this. Now let's go ahead and see what we can find with this one. Okay, so here again we're going to do the Pearson's R, and we're going to do the Pearson's R squared. Let's go ahead and calculate this. So down here we're going to say equals CORREL. And go ahead and pause the video if you want and see, if you can figure out how to do this, if you want to, because I think that would be pretty great practice. So please pause if you would like. Oops, sorry, I need to do my y value first. It honestly really, it doesn't really matter, but B13, B19. Those are allergies. A13, A13. Okay. Wow, yeah, that's pretty high. And then this is D14. And yeah, that's what I thought. Okay, so, and it makes sense, right? Fat is lipids full of calories, right? Tons of energy. So this makes a lot of sense. So if we look at the Pearson's R&R squared for this correlation, wow, that is so close. And that means that we should expect to see an extremely high positive correlation. In other words, as the fat increases, the calories increase, which definitely makes sense. And then the Pearson's R squared shows that we have a good fit. And the amount of variation in our Y variable is explained far more than just the average noise that we would expect. And so this seems to be very highly significant. What if we were to make a graph of this to see, well, we should expect to see a pretty strong positive correlation, and I bet if we go ahead and we make a graph of this, I bet we're going to see a crazy, yeah. So now, of course, the data isn't fitting very well, but we can go ahead and, I guess we could go ahead and add a line of best fit if we wanted to, and I am, of course, going to forget how to do that the second that I really, really need it. I'm sorry, guys. This is embarrassing. Trend line. There we go. Yep, and so we can see we have this nice positive trend line going up here on the scatter plot. And of course, we need to change the x and the y in order to get it, more centered here. But other than that, this is basically what we see. So positive correlation, that makes a lot of sense. So that's how you do a Pearson's, right? And Pearson's correlation, very easy, really, really good to do with your data, especially in your IA, to show the relationship. Now, let's go ahead and take a look at chi-square, because chi-square was the other family that we were looking at. So chi-square is basically going to be comparing two qualitative data points together, right? So non-continuous. And let's go ahead and take a look at the DASL. We'll go down, scroll down until we see chi-square. Here it is. All right, we'll go to ball player births because this is a pretty small number of cases and I feel like it's manageable. So if we go to ball player births, essentially it's suggesting that children born in the summer have an advantage over their peers when it comes to sports, maybe because they can go outside when they're young. The data report the number of professional ball players born each month, blah, blah, blah. Okay, so basically if you're born in the summer, you're better at baseball is basically what they're trying to say. Now, that seems like total malarkey to me, but let's go ahead and see whether or not the two guys are related. Now, again, these are qualitative variables because the month of the year is a qualitative variable. Even if you express it as a number, right? It's basically saying, oh God, July, November, God, this is harder than I thought, June, October, anyway. So these numbers represent months, right? And then these ball player counts. I'm going to guess the ball player count, like, I'm guessing that born in each, oh, this is the number of ball players that are born in each month. Okay, all right, I see. So basically it's saying 102 ball players were born in the month, in this month. And this is not a continuous variable because it's not going to be like 102.2 children born. I mean, you hope not, right? Because you don't want 0.2 of a child. Anyway, so we have these two qualitative variables, non-continuous variables that we're going to go ahead and take a look at. So, all right, so how do we do this on our spreadsheet? Well, in order to do this, we're going to go ahead and need to figure out a couple of things. So if you look at our formula, for chi-square. Chi-square is this, equals the sum of your observed values minus your expected squared over your expected. Now what the heck does that mean, observed and expected? Observed is what you actually see in the field. Expected is what you would expect to see. Now, how do you come up with the expected? The expected is usually like a null hypothesis. In other words, it's like what you would expect to see if there was no relationship. Or if you have some sort of model that you already know kind of explains your situation, you might use that. So like, I don't know if you guys remember we did this chi-square with genetics testing where we were looking at, kind of what we would expect to see in terms of certain genes like sickle cell anemia being expressed within a population that was ravaged by, malaria, infested mosquitoes, right? So like in that case, we have some methods of being able to guess as to which what ratios of these alleles we should see in the population using, Mendelian genetics and that dihybrid cross and all that stuff. But anyway, if you don't remember that, that's totally fine. Just gobbledygook. Let's go on. So to do chi-square, we need to go ahead and so we got our observed values. So we have these are our observed values. This is the number of ball players that we see for each of these months, right? So these are observed values. So is there a difference between, the number of ball players that are born in any one month? Well, here's the thing: is like that's our observed. So what would we expect if there was no relationship between the month you're born and whether or not you become a baseball player? Well, what we would expect is that there would be an equal number of baseball players, or generally an equal number of baseball players per month. right? Okay, for all months. And so if we just take the average of this number of ball players, which is 118, I already did the math, just add them up and divide them by the number of data points, you get 118. We would expect that maybe 118 ball players would be born every month, and it wouldn't matter what in the heck, month they were born in, okay? So that could be our expected value. So let's go ahead and sort of show you how we're plugging that in. So we're going to start here with our observed. All right, these are our observed data points, and then we're going to have our expected. Okay, and then we're going to go down sort of the line and break this equation into smaller pieces. So then we have observed minus expected, O minus E, and then we have observed minus expected squared. So we say O minus E squared, and then we're going to have, O minus E squared over E, right? Okay, and then we're going to have the sum of all that at the end, which I could put here or down here. I'll probably put it down here. So here's all the different things, all of the different sort of columns that we need to follow. So let's check out our observed first. We're given our observed. So these are our observed. So 102, 105, 114. Should have written these out beforehand. I really apologize. 115, 116, 121. You can just skip ahead and when I'm done with this, I apologize again. 121, 122, 126, 134. All right, cool. And then down here for the expected. Now the expected I said was 118 all the way across the board, so I'm just going to kind of 118 is what I expect, and down here throughout all of them. Okay, good. So we've already covered all that. Now I know there are two other data points here, and I'm ignoring them right now because this is an example. Obviously, in your real life example, you would want to use all your data points. So then I can go ahead and calculate O minus E. This is where the spreadsheet comes in so handy because it just does everything for you, and it's wonderful. So O minus E, how do we calculate that? Well, here's our O and here's our E, so I want to take this and subtract this away from it. What do I do? Well, I say equals, and then what cell is this? This is A23, okay? So A23, all right, minus, I'm going to say B23, because that's my expected over here, so B23. So this cell minus this cell equals, bam, negative 16. What I can do is just grab this little square, and it applies that formula all the way across for all of them, and that's all I have to do. Oh, now all I have to do is square everything in this column. Okay, so this squared, all right, so how do I do that? Equals, what is this cell? C23, all right, C23. Whoops, I need to put that in parentheses, and then go ahead and square it. And bam, I get that. So then I'm going to go ahead and come down here, drag that down, boom, already got that. Now I come over here, O minus E squared, which is what I got here, divided by E. So all I have to do here is I have to say equals, and this is all my O minus E squared. So I can just say equals, and start here with D23, say D23, divided by, your little slash mark there, and then my expected, which is going to be B23. And bada bing. And look at that. Now, of course, your chi-square value is the sum of all of these numbers here in that. And what do? I say equal sum, and then I go ahead and say my values. I can't see them, however, because, all right, what do I got here? I got E23 through E32. That's easy to remember. So E23 through E32. And there is my chi-square value right here. So this is my chi-square. Now what the heck does it mean? Okay, so in order to actually calculate our chi-square, we need to have the significant values. Now I was a dummy and I didn't put this on the website here, so you can just Google it though. You can say chi-square critical value chart. Scroll down, here's one. Scroll down, they're everywhere. So anyway, so here we have our degrees of freedom over here, which is good, and then we have probability less than the critical value. So remember, in terms of most science, we want a probability of 0.95 or higher, right? So less than 0.05 if you're thinking about it the other way. So anything this column and to the right we would count as significant. Anything to the left we would not. Basically we're saying that if it's to the left, if it's here or to the left, we're basically going to say, well, it's probably just due to random chance and it's not actually significantly correlated. If it's from here over here, then we're going to say that it's probably not due to random chance and they may be significantly correlated. That's a bit of a lie, I'm going to say, but we're just going to kind of say that for now, and I'll talk about why p-values suck later on. Just go with it for now. So we're going to figure out a degree of freedom, and I'm sorry, I'm pretty sure I skipped the degree of freedom thing before. So your degree of freedom is basically the number of total data points that you have. So you're n minus 2, okay? So capital N minus 2. So here we have 20 data points, right? So our n equals 20, right? And so n minus 2 equals 18 is our degree of freedom. Up here for this one, we had 14, I think, so n equals 14, and then our degree of freedom would be 12. And I need to go ahead and say this is our, yeah, so our degree of freedom equals 18. All right, yeah. Okay, and so for this one up here, to determine our significant value, sorry, I'm sorry for bringing this back up here to this one, but for our correlation, our significant value, if we were using this one right here, and we had a degree of freedom of 12, if we went back to this correlation thing and we scroll down enough, we'll see this. We go over to the degree of freedom of 12, and we go over here, and it needs to be at least 0.533 in order to be significant. 0.661 if we want it to be 99% significant. Which is, again, kind of a lie, but we're just going to kind of go with it right now. And so if we look at that, is it? Yes, it's above those numbers, so yes, we're significant. Now over here to the chi-square, we have a chi-square of 6.84. We have a degree of freedom of 18. So let's go over here to this chart, go over to 18. Degree of freedom of 18, oof. All right, degree of freedom of 18, if we take a look at this, you need 28, right, or higher in order to be accepted. And so here, we are not going to be able to reject our null hypothesis. We're going to have to fail to reject our null. In other words, there is probably no relationship between the month that you're born and you know, whether or not you become a baseball player. So this is how you do chi-square, and this is how you do correlation. You can notice that they're very similar in the ways that we were able to kind of, even though the formulas were different, we were able to use a spreadsheet, compile the data, come up with an answer, and then sort of see whether or not it was significant. Again, significance with p-values, you have to be very careful, and we're going to go over that later on, but just, you know, be very aware that it's something, you know, that you really want to be careful about. So anyway, that's how you complete this. So I hope that helped. Please choose your own data sets and crunch the numbers. Let me know if you get help, if you get stuck, and I will help you out. But otherwise, I hope this helped, and have a great day, guys.